So yes, I'm very pleased to be introducing Chris Bishop, who I've known for about 15 years now. And I remember as a senior graduate student visiting his lab at Aston University and telling him in a rather excited fashion about factor graphs. And 15 years later, factor graphs have appeared in his later book and are now part of Infer.net. So it's been a very successful collaboration. So Christopher is a professor of computer science at Edinburgh and, of course, the chief research scientist here at Microsoft Research, Cambridge. He's a fellow of various institutions, but he's best known for his work in machine learning and, of course, for the Christmas lectures which he gave last year in 2008. So please join me in welcoming Chris Bishop for the last section of today.
So I'm going to talk to you about some developments in the field of machine learning, and help if I have some slides. There we go. These are developments which have really happened over the last 5 years, which I think are hugely important and will be very exciting for machine intelligence over the next 10 years or so. They're not things that I've developed, and they're not things that Microsoft Research has developed. They're things which, or ideas which have emerged from the worldwide research community. However, Microsoft Research is very much at the forefront of these developments. So I'm going to tell you about a new paradigm for machine intelligence. And to give you a bit of context, let's begin by looking at a little bit of history. So if you go back to the 60s and the 70s, there was a great interest in artificial intelligence. And there's a lovely quote here from Minsky, who's one of the founding fathers of the field. He said, "Within a generation, the problem of creating artificial intelligence will largely be solved." Well, of course, that didn't quite come about. Now, why was that? Well, all of the emphasis at the time was on techniques called expert systems, based on rules obtained from human experts. It was based on background knowledge, on domain knowledge, domain expertise. And one of the challenges this faced was the explosion in the number of rules that were required to tackle complex problems. So while expert systems proved very useful for certain specific applications, they didn't turn out to be a panacea. So let me characterize that phase of the field as an emphasis on systems built using handcrafted rules, using domain expertise. If you move on to the 1980s up till the present time, more or less, we see a very different emphasis. The emphasis was much more on statistical models. For example, neural networks, support vector machines, and hundreds of other similar models. And these proved to be rather more successful. Here's just one example out of many thousands. This is the handwriting recognition system from Tablet PC, which pretty much achieves as much as you could ever expect to achieve at the signal processing level. Its performance is extremely good. So neural networks and other statistical techniques achieved many successes, but one of the challenges is that it's difficult to incorporate complex domain knowledge. These are black boxes, and it's very hard to modify the black box to build in your expert domain knowledge. So I'll characterize this phase of the field as an emphasis on black box statistical models. So what I'm going to talk about is a new paradigm for machine intelligence, and the goal of this is to find a deep integration between domain knowledge and statistical learning. Not to sort of kludge the two together, but to find a paradigm, a principled framework in which we can integrate expert human domain knowledge with statistical learning from data, including particularly the very large data sets that are currently emerging. So this is based on three key ideas. So what are these? Well, first of all is the idea of using Bayesian learning. So the idea of Bayesian learning in principle is actually very simple. We use probabilities to quantify uncertainty, and we manipulate those probabilities using the very simple sum and product rule of probability theory. So if we have a quantity that we're interested in called theta, and we have some information, let's call it x, might be data, might be background knowledge as well, set of information which tells us something about theta, then we quantify our uncertainty in theta using a conditional distribution, the probability distribution of theta given x. If we now observe some new information, for example, some new data, let's call that new data x hat, then we can incorporate the effect of x hat using this function. It's called the likelihood function. And all we do is take this initial distribution, we'll call that the prior distribution, and we multiply by the likelihood function. And that gives us a new distribution of a theta called the posterior distribution. And typically what happens is that as we observe new information x hat, it narrows the distribution, our uncertainty is reduced, and that's what it means to learn in a Bayesian setting. So in principle, Bayesian learning is actually very simple. Notice that it's also very sequential. If more information arrives, we compute the new likelihood function, multiplied by the current distribution to get the new distribution. So that's the first key idea. The second key idea is called probabilistic graphical models. And just like Bayesian learning, this concept goes back for many, many decades, but it's undergone a lot of development in recent years, and Brendan Frey mentioned factor graphs as one particularly important development. This shows a simple directed graph. So it's a graphical description of the probability distribution, in this case over three variables, x1, x2, x3. And the arrows describe the relationships between those variables. And these graphs have a very specific semantics. They describe the way in which the joint probability distribution over all the variables in the graph factorize into small local distributions involving small subsets of the variables. And it's through the structure of the graph that we capture background domain knowledge. So domain knowledge is expressed through the structure of the graph, and then statistical learning, Bayesian learning, is used to work out the local distributions at the nodes of that graph. The third thing we need, particularly if we're going to scale to very large data sets, is a very efficient way of doing inference. That is, an efficient way of doing these probabilistic calculations on these graphs. Now, the key idea, or one of the key ideas, is the following. It's very simple. It's to exploit that factorization. So a graph describes the way a distribution factorizes. We can use that factorization to do very efficient computation. So here's a little model of what this looks like. Imagine we've got a quantity, x times y, and we're asked to compute the sum of this over all values of x and all values of y. And for simplicity, let's suppose that there are just two states for x and two states for y. This is very simple. Here's an expression for that sum. And this expression involves 7 numerical operations, 4 multiplications and 3 additions. But we can exploit the factorization of the function x times y to rewrite this in a form which is mathematically equivalent, but numerically is much more efficient. So this second expression involves just 3 operations, 2 additions and 1 multiplication. So it's mathematically equivalent, but computationally much more efficient. And we'll do that with complicated models using our graphs. We'll express computations which in principle may be exponentially costly in terms of local computations on parts of that graph representing the factors. And in that way, we can reduce computations which may be exponential to computations that may be, for example, linear in the size of the graph. So that's the third key idea. And it has a very elegant graphical interpretation. Because these computations are local to those factors, we can interpret the computation as the passing of messages locally on the graph. So in this simple example, let's suppose we have 3 variables, and we'll shade in this node to indicate that this variable has now been observed. We've gone out and we've measured it, so that's some data. And because we've observed some data, we now have to update the distributions over the other variables using that little formula that I showed you before. And that can be done using local message passing. So we might pass a message up here, and then afterwards pass a message down here. And now we're able to update the distribution over this variable in light of this new information or this new evidence. And that's very important because, again, that contributes to the efficiency of the computation, and indeed we can structure our software in terms of this local message passing on the graphical structure. There's one more problem that we have to face, which is that so far I've shown you a little example in which we did a summation over those 2 variables x and y, and that's typically the computation that we need to do. We need, in a Bayesian model, to do summations or integrations. But what happens if those integrations are not tractable? And in fact, in most models of practical interest, they're not. So let's suppose that our model describes some complicated distribution that I represent schematically like this. Well, suppose that distribution is too complex to have a closed-form analytical solution. We can't make exact predictions with that distribution because it's too complex. Well, up until a few years ago, there was really only one tool in the toolkit, or one set of tools, based on sampling, typically Markov chain Monte Carlo methods, which would aim to draw a set of samples independently from that distribution. Once you've got that set of samples, then integrations, so integrations along this axis here, become simple summations. And of course, I'm showing you a one-dimensional example. In practice, the number of dimensions is the number of nodes in the graph and can be extremely large. So Monte Carlo methods are wonderful because they're very flexible, they're very general purpose, but they're computationally very intensive. So good applications involving Monte Carlo have typically been limited to a few hundred or a few thousand data points. If we want to scale up to millions or billions of data points, then we need a very different approach. And a whole set of these have been developed over the last few years, and they have various names: variational Bayes, Loopy belief propagation, expectation propagation, and many others. And they have the following characteristic: they represent deterministic approximations. So we take our true but intractable distribution, the red distribution, and we approximate it by a family of simpler distributions. And in this illustration, I've just indicated that by simple Gaussian, the green distribution. So that's a family of distributions, and now we explore that family to find the member which is the best approximation. So in my little toy example here, we might adjust the mean and the variance of that Gaussian until it represents the best fit to that red distribution. And according to the way we do that optimization and according to our definition of what constitutes the best fit, we can arrive at a variety of different algorithms. And these are computationally much more efficient and they scale well to very large data sets. So those are essentially all the ingredients in this new paradigm, this new framework for machine learning. So let me now give you a very simple tutorial example in which we put all of these ingredients together. So let's consider a simple representation of a drug trial. So we've got a group of participants. Everybody in this group has some kind of disease. And we develop a new drug. We want to test the drug. So we'll give at random some of the people the drug, and everyone else will give a placebo. And then we wait, and some of the people will recover, and others will not recover. And the question we want to know is the drug effective? In other words, is it different from the placebo in a way that's statistically significant? So let's, first of all, build a probabilistic graphical model which captures the structure of this problem. So we'll introduce a binary variable, which is 1 if the drug and the placebo are different, and it's 0 if they're not. And we'd like to know the probability that they're different once we have all the data. If this binary variable is 1, in other words, if the drug and the placebo are different, then we switch over to the left side of the graph, and if they're the same, we switch to the right side. This is a construction, a graphical construction called a gate. So first of all, let's suppose that the drug and the placebo are different. That means there are two separate probabilities. So we introduce two more variables, two more nodes in the graph. The left one is the probability of being cured if you're treated with the drug. And there's another probability, which is the probability that you'll be cured if you take the placebo. In other words, you would have got better anyway, even without the drug. Now we have our patients. So each of these people has the disease. Some of them are given the drug. Some of them are given the placebo. Now, those patients who are given the drug will recover with a probability governed by this variable, and those who are given the placebo will recover with a probability given by the other variable. Now, on the other hand, let's suppose that the drug and the placebo are actually the same. They statistically behave in the same way. Then all of these people share a common probability. There's a single probability, which is the probability that you will recover, and it doesn't depend upon whether you take the drug or the placebo. So in this case, the probability of recovery is governed for everybody by this same variable. So that's our graphical model. That's the first stage, is to construct the graph. The next stage is we collect our data. We make observations, and we'll suppose that these three people recover from the disease, and these two people don't recover. And now we want to know what is the posterior probability distribution for this variable different at the top, given that we've seen all this data. And we do that with a message passing algorithm. So we pass messages around on this graph, iterating until we reach some form of convergence, and now we can read off the probability that the drug and placebo are statistically different. So let me just show you a little demonstration of what this looks like. So the top row here represents the people who took the drug, and the bottom row represents the people who took the placebo. And on the right-hand side are these variables, which is the probability of being cured if you took the drug and the probability of being cured if you took the placebo. Now, that probability is a number between 0 and 1. We don't know what it is, so because we're Bayesian, we characterize that uncertainty using a distribution. So this shows the distribution over the probability of recovering given that you took the drug, and similarly for the placebo. Now, that distribution is just flat because at the moment we don't have any data. We will in a moment. The other thing to look at is this variable here. This is corresponds to the top node of that graph. This is the probability that the drug and the placebo are different. At the moment, we've just set this to 0.5 because we have no idea. Once we observe data, we'll see how this moves. So up here means we're certain that they're the same. Down here, we're certain that they're different. So let's see what happens when we collect some data. So let's suppose that we have some people who've taken the drug and they've recovered. Some other people have taken the drug and they haven't recovered. And down here are some people who've taken the placebo. We'll imagine that a few of them have recovered. Perhaps rather more of the people who took the placebo actually didn't recover. And you can see, as we introduce more and more data, as we change the data, we're constantly in the background rerunning that message passing, rerunning that inference, and updating these distributions. So what we see here is, I think, intuitively reasonable. Of the people who took the drug, the majority actually recovered. So the probability of recovery has a distribution which is skewed towards the right. For these people, the majority of them actually didn't recover, and so the distribution of the probability of recovery for people who took the placebo is skewed to the left. And over here, we see that this probability has changed. This has moved towards being different. So there's some evidence here that the drug and the placebo are acting differently, but we're by no means certain. If we were to observe a lot more data, we'll see what happens. We see the distributions shift further, and we see that also they tend to narrow. As we observe more data, the distributions narrow. That means we're learning from the data. And by the time we've seen this amount of data, we're getting really very confident that the drug and the placebo are actually different, and that this difference in these observations did not come about by chance, that there's a real effect there. Okay, so that's a simple toy example of this paradigm in action. So let's move on now and look at a real-world example. This is some work which was done by colleagues of mine in the machine learning group at Microsoft Research in Cambridge, and they developed a general algorithm based on this paradigm for solving ranking problems in a Bayesian context. So the problem we want to solve is to obtain a global ranking from noisy partial rankings. Now, a good example to think of here is a chess club. So imagine we're all members of a chess club. We play games of chess with each other, and we want to work out who's the best, who's the second best, and so on. We want a sort of leaderboard. The data we have is the results of games of chess. So two of us play a game of chess. One person wins, one person loses. We have lots of these pairwise rankings. We want to use the pairwise rankings to construct a single global ranking. It's a noisy problem because if you're a stronger chess player than me, you'll win most of the time, but occasionally I, as the weaker player, will win. So those are noisy partial rankings. And so this is a very elegant general problem for solving that problem. And this is contrasted with the conventional approach. The conventional approach is called ELO. It's been around for a long time. It's used in chess worldwide. And in the ELO system, every person is assigned a strength. And as a result of a chess game, the winner will have their strength value increased a little bit, and the loser will have their strength value reduced. So every player has a single number. In this Bayesian approach, we're uncertain about the true strength of a player, and so we describe that by a distribution. In this case, a simple Gaussian distribution. So everybody has a strength and an uncertainty in that strength. And as they play more and more games, their strength will evolve, and the uncertainty in that strength will reduce as we gather more and more evidence. So first of all, we construct a graph. Let's just consider two players, 1 and 2, and they play a game against each other. These nodes represent their strengths. They're described by Gaussian distributions, and they start off with very broad values because we don't know the player's true strength at the start. They play a particular game. On this particular game, each player delivers a certain performance. This is the performance of that player on that particular game. Again, that's noisy because I may be a good player, but some days I do well, some days I perform less well, and so that's captured by this distribution. So this is a graph of the performance of player 1 and player 2. This point here is the strength of player 1, this is the strength of player 2, and their performance is a Gaussian distribution centered on that strength. Now they play a game of chess, and we observe the data, which is the outcome. And let's suppose that player 1 is the winner. So this is now going to be an observed node in which player 1 wins the game. And if we look at this, in our model, a player wins if they have the higher value of performance. So what that does to this distribution is it sets to 0 everything above this horizontal line. So that red region has all been set to 0, because that's the region in which player 2 has the higher performance. This blue region is where player 1 has higher performance, so that's the region in which player 1 is the winner. So that's modified the distribution. It's also made it non-Gaussian. And the approximation, as I indicated earlier, that we're making here, is to map that non-Gaussian distribution back to a Gaussian. So we find a Gaussian which has the same mean and variance. This is using a technique called expectation propagation. Now, in reality, of course, we have a much more complex situation. And this example shows a game, in fact, two games involving teams. So this middle team has players 2 and 3. This team just has player 1. This team just has player 4, sorry. And these two teams each have a performance, and they play a game against each other. And these two teams later play another game against each other. So no matter how complex this is, we can always construct the graph. And lots of advantages here. One advantage is that ELO doesn't work for team players. In ELO, you can't assign the credit. When the team wins, you don't know which person was responsible for that victory. Whereas here, we can easily extend to team games just by drawing the graph, as you've seen. There are much bigger advantages to be had by going to this Bayesian approach. Here's an example of some data obtained from Xbox on a game called Halo, and this shows, along this axis here, is the number of games that are being played. So it goes from 0 up to 400. This is the number of games that are being played, and there are lots and lots of players involved in this. Let's just look at two of them. One of them is called Char, one of them is called Sequel Wildman, and this is how, under ELO, their strengths evolve over time. So as they play more and more games, the ELO algorithm is updating their strength, and we can see their estimated strength is improving through time. If we go to a Bayesian approach, we see something very different. We see much more rapid convergence. In fact, this system converges in the sense of how many games have to be played, how much data has to be gathered, about an order of magnitude faster than the ELO system. Let me just take a moment to give you some intuition as to why that is. Let's go back to the situation where you and I are playing a game of chess. Let's suppose that I'm the weaker player, you're the stronger player. Let's suppose I'm 120, you're 130. Now in ELO, if I win, my score goes up a little bit, your score goes down a little bit, and then we play the next game. But let's suppose we're doing Bayesian ranking now, and my score is 120 plus or minus 20. It's very broad. We're very uncertain about my true skill. Let's suppose your skill level is 130 plus or minus 1. So you've played lots and lots of games. We've really narrowed it down. We know your skill very precisely. If I'm 120 plus or minus 20, I beat you, and you're 130 plus or minus 1, you can see we can make a very big change to my score. My score must be 129 at least, because I've just beaten somebody with a high score and a narrow distribution. And that intuition, of course, happens automatically. When we apply the rules of probability, those big changes are made when they're justified. And it's those big changes that lead to this much more rapid convergence. And it's because of that dramatically improved performance by going to a Bayesian approach that this system was used on Xbox Live. Now, the original Xbox games console, the online service used ELO up until the launch of the Xbox 360. When Xbox 360 was launched, the online service was switched over to this Bayesian ranking system, which we call TrueSkill. And that was launched in September 2005 and is used for ranking for all Xbox 360 live games. That's used, first of all, to provide a leaderboard, so you can see who's the best player, who's the second best, and so on. But it's also used in real time for matchmaking. What has to happen on Xbox Live is if you ask to play a game of Halo or whatever it may be, then in a very short space of time, the system has to match you up with other players around the world who have similar skill levels. This allows us to estimate those skill levels very quickly and efficiently, and therefore to find good matches, which gives people a very good gaming experience. And the numbers for this are quite impressive. This involves millions of users, millions of match outcomes per day, and this has been running 24 hours a day, 7 days a week since the launch of the Xbox 360. So I think this represents one of the first, possibly the first, what I call planet-scale application of Bayesian inference. So Bayesian inference has really come of age. We're no longer just looking at a few hundred or a few thousand data points in a sort of offline scenario using Monte Carlo methods. We now have real-time online inference involving millions of data points. Let me finish by just showing you briefly one other application, a very different application. This is very recent work, and this is collaboration between my group at Microsoft Research Cambridge and the University of Manchester. We're trying to understand the genetic and the environmental causes of asthma, which is a very important, one of the big chronic diseases of childhood. So we have a wonderful data set which has been collected over the last 11 years. It involves 1,000 children. For each of those children, we've been collecting 2,000 variables, all sorts of environmental and phenotype information. You can see some of this information listed here. Lots and lots of tests. Every 2 years, each child is brought into the clinic and subjected to a huge battery of tests, skin tests to measure their allergic response, blood tests, their breathing is measured using a whole battery of different tests, and so on. Questionnaire data is taken. So we have 2,000 variables per child, and we've now recently also collected a very impressive data set of genetic information because we've obtained nearly 700,000 so-called SNPs, single nucleotide polymorphisms, little genetic markers for each of these children. So we're in a very good position now to look at the interactions between genetic variability and the environment in trying to understand this very complex and as yet very poorly understood disease. So don't worry about the details of this graph, but this graph represents the domain expertise. This was constructed over a period of several months by having very, very detailed discussions with the consultants, the clinicians in Manchester to try to understand what they know about the variables that are important in asthma and the way they relate to each other. So we've captured that background domain knowledge using this graph. And this is actually not a graphical model yet. This is a sort of block diagram. The actual graph is much more complex. So if we just look at this little piece of the graph, which has to do with the sensitization to allergens like peanuts and furry animals and so on, we can turn that little piece of this block diagram into a true probabilistic graphical model, in this case involving many tens of thousands of variables. So you can see there's a tremendous amount of structure in this graph which represents that domain knowledge. But now we use our large data set combined with these fast, efficient inference algorithms to do statistical learning in order to learn the details of those distributions. So I hope this gives you a feeling for what I mean by a deep integration between rich domain knowledge and statistical learning from large data sets. And just to give you a little preview of one interesting result we've obtained is the following. These represent 5 clusters of children which have been found automatically from the model which I described earlier, and the data used here was just the allergic sensitization data. No information about asthma was used, but now we can look at the clusters and look at the proportion of children in each cluster which has asthma. And you can think of the asthma roughly as corresponding to the red bars in this histogram. And we see that around, well, over 40% of the children in this cluster have asthma, as compared with around 22% using the current clinically recognized and internationally used definition of allergic sensitization called atypy. So we're excited because with techniques like this, we hope, we're discovering some true underlying phenotypes, not simple observed phenotypes, but complex ones which underlie the disease. So we know that asthma is a complex disease. It doesn't have a single genetic cause. And people have struggled over the last 10 years to understand what the genetic causes of that disease should be. There's no clear pattern. Our hope is that we'll see much better correlation between genetic variability and these latent classes, which we believe are more representative of the disease, that have been seen previously simply by correlating genetic variability with the presence or absence of asthma. So we're very excited by this project. Finally, let me mention that if you're interested in playing with this new paradigm, I'm very pleased to report that we've released a software toolkit, a very sophisticated industrial-strength toolkit called Infer.net. This has been available for over a year now. It has a very large number of users. It has a strong user community. People are invited to contribute. For example, if you develop new factors or new distributions, you can contribute these to the user community, and this is available freely for non-commercial users. So just go to research.microsoft.com/infer.net, download it for free, and there's very comprehensive documentation and a strong online user community. So I encourage you to do that. And finally, then, let me just wrap up by summarizing, I think, the key messages. First of all, I've described what I see as a new paradigm for machine learning, something which I think will become of enormous importance over the next 10 years in a huge range of different applications. It's based on three key ideas: a Bayesian formulation in which we use probabilities to describe uncertainty in a mathematically consistent way. It uses probabilistic graphical models, that is, graphs which describe the relationships between the variables in our model, and it's the structure of that graph which captures rich background domain knowledge. And then finally, over the last few years, we've seen the emergence of some very fast deterministic inference algorithms which allow us to do approximate but effective inference on these graphs using local message passing in a way that scales to extremely large data sets. And we now have applications that involve literally several billion data points, online applications. So the key to this then is this deep integration of domain knowledge with statistical learning, which is something that's not really been available to the machine learning community up to this point. And so I think the potential for this paradigm is very great. And then finally, you can get started by downloading Infer.net and start to play very quickly with some of these models for yourself. Okay, thank you very much.
So questions as usual, walk up to this mic. There are two here, one in the middle. Oh,
hello?
Yeah.
Okay. I've got a question for you. What about if the graph has cycles? In all of your examples, there weren't any cycles.
That's a great question. Thanks, Brendan. I think you know the answer to that one, but for everybody else. So it turns out if a graph doesn't have cycles, if it's just a tree structure, then provided we can do the local calculations at each node, we can solve it for the whole graph. We can solve any inference problem for the whole graph in linear time. We just do one pass through the graph and then one pass backwards through the graph, and we have exact inference. But for most problems, including the examples that I showed you, we have loops in the graph. We have cycles. And there are various techniques for dealing with this, but one very simple technique, which is just called Loopy belief propagation, is to apply the same algorithms anyway. Just keep sending messages around the graph, and if you do it in the right sort of way, you find that it converges for most problems of practical interest and gives very good inference. So for most of the examples that you've seen, or all the examples that I've shown you, we have to iterate and pass messages around the graph a number of times in order to get good inference and good convergence. But in practice, we find that this works remarkably well. And one of the theoretical challenges, actually, in the field of machine learning is to try to understand why it is that some of these inference algorithms work as well as they do, because that came as something of a surprise to the community and is the subject of a lot of very intense theoretical discussion and research at the moment.